All right, hello everybody. I thought I would do a little bit of extra practice with the phase diagrams and the lever rule, since we didn't really have a ton of time in lecture to go over them. And you know, never hurts to do some practice, just to kind of clarify some stuff. So this is our good friend, the copper-silver phase diagram, right? We have temperature on the y-axis. We have composition in weight percent silver on the x-axis. Right? We also have atomic percent silver on the upper x-axis. And this guy, they also give us Fahrenheit on the y-axis if you're feeling crazy and want to deal with Fahrenheit. It was mentioned during the lecture, and it's important to note, right, when you're talking about compositions, are you talking about atomic percent or weight percent, right? Because depending on the atoms present in the alloy will depend on the scale range. Silver is quite a bit heavier than copper, so we end up seeing that the atomic percent scale, right, does not match the weight percent scale. It's a little bit offset, not significantly, but it does matter, especially if we're trying to create or analyze an alloy for properties. We want to know which of these we're talking about. So we're going to deal with weight percent for all of these, but we could just as easily deal with atomic percent as well. So we have pure copper on the left, right, pure silver on the right, and a linear increase from left to right. We have our pure alpha phase, or our alpha phase on the left side here, right? This is a single phase of copper with a small amount of silver. We have our beta phase, which is silver with a small amount of copper, right? And then we have our kind of pure liquid single phase. And then everywhere else, right, here, here, and here, we have two phase regions, okay? So just kind of moving about this diagram, we see at around 800 Celsius at these kind of elevated temperatures, right, we can add silver atoms to copper, the unit cell, right, through a substitutional, and we can have alpha, alpha, alpha until we get to around 8% silver. At that point, we start to form a secondary phase in our microstructure, right? For temperatures above this eutectic temperature, right, above 779, our secondary structure is a liquid phase. For temperatures beneath that, our secondary structure is a beta phase, right? And the same thing applies on the opposite side as well, right? So it's important to note the condition, because that can kind of help you know how much of each phase you can have and how much you can dissolve inside, because we see the amount of silver we can dissolve in copper decreases, right, as our temperature decreases. Okay. All right, so let's, if we're in any of the single phase regions, we know the microstructure is 100% that phase, right? But what happens if we're in a two-phase region, right? Let's say we're in alpha plus beta, and we have an alloy which is, say, 600 degrees Celsius and about 40% zinc. So I'm going to use a straight edge here to give me that, try to be mildly accurate. So right about here, right? So there's a point right there, right? This is 40%, I'll say weight percent silver, right? And it's 600 degrees Celsius. Okay, we know this alloy, this microstructure should consist of alpha plus beta, but we don't know how much of each is present. So to solve that, we have to use the lever rule, right? So I'll just write it up here. All right, the lever rule, this gives us fractional amounts of each of our two phases, okay? So the first step of the lever rule is we need, I'll just put step one up here, we need a tie line. Okay, so the tie line is a horizontal line which connects your alloy to the two single phase regions it connects to. So I'm going to draw a horizontal line through my point from the alpha phase all the way to, right, the beta phase. Okay, so a little bit of smeary, that's fine. Okay, so where it connects, we can figure out the composition of our alpha phase. So where it connects with the single phase region, we draw a line straight down to the composition axis, right? And where it connects with beta, we will also draw a line straight down. There we go. And then we already know the composition, but we'll draw a line straight down here as well. It's a little bit off from 40, but that's okay. So with these three lines, we know some compositions, right? We know the composition of our sample, right? We can call this C1 or C naught. We know the composition of the alpha in our two-phase region. So this tie line tells us the composition of the alpha phase, so C alpha, right? And looking at that, that's probably around, I'm gonna say 4% silver. And then here, we know the composition of the beta phase in our two-phase region, right? So this is C beta. And that's probably, I'll say 96%. Silver, sorry, it's a 96. Okay, so we now have a C alpha, a C1, which is 40, and a C beta, which is 96. Okay, so the lever rule, we need to use basically the lengths of this line to help us figure this out. So we can break this line into two sections, right? The first is the length from alpha to C1. We can call this A. The second section is the length from C1 to C beta. We can call that B, right? And the full length of the line is A plus B, okay? So the lever rule, we then need to use our, basically it is a length ratio, right, equation. So the way the lever rule works is it's kind of like a seesaw. You basically say how close you are to one side versus the total length of the sample. So the basic system is the fractional amount. So we can say, let's see, the fractional amount of alpha in our system. It is the length of the opposite side from alpha divided by the total length, right? So it's going to be B divided by A plus B, right? Similarly, the fractional amount of beta is going to be A length over A plus B, right? So it's just the opposite. Now, we know these lengths, right? The length of B is just the length in compositions, right, from C beta to C1, right? So it's going to be C beta minus C1, right? And A plus B is going to be the total length of the line, C beta minus C alpha. Similarly, for fraction of beta, we need the length of A, right, which is just going to be C1 to C alpha, right? So C1 minus C alpha. And again, the full length of the line is going to be C beta minus C alpha. Okay? So we can plug these numbers in. For a fraction of alpha, right, we're going to get 96 minus 40 divided by 96 minus 4. Right, and this would give us 56 over 92. Right, and then for beta, it's going to be 40 minus 4 divided by 96 minus 4, right, which would give us 36. Sorry, this should be 52. 36 over 92. Nope, still that's 56. 56 over 92 divided by 36 over 92. Yeah, so 56 plus 36 should add up to 92. Okay, so our fraction of alpha, right, is 56 over 92, which I have a calculator here. 56 divided by 92 is about 61, so 0.61, right? And our fraction of beta is 36 over 92, which should be, yep, around 39, 0.39, right? So if we turn this into a percent, right, 61% for alpha and 39% for beta. Right, not too bad. So really, you just need the tie lines. you draw a line straight down, and then you do the ratio. And you can do this for basically any two-phase system, right? So the lever rule gives us the fractional amount of each phase. The tie line gives us the composition of every phase present, which is quite nice. All right, let's do another example. Okay, let's take, I think the one from class. We'll do one from class. Let's say 900 degrees Celsius, right? So I'll put 900 here, and let's say 30% zinc. Sorry, 30% silver. So right about here-ish, right? So this is going to be 900 degrees C and 30 weight percent silver, right? Okay, so I would like to know what is our fraction of liquid phase. Okay, so we're trying to figure out a fractional amount, so we're going to use our tie line. So I'll draw my line that connects through my point at 900. All right, so there and there. Okay, we will draw our lines straight down from where they intersect our single phase regions. All right, there's one. All right, this one's 30. We already know this, but we'll draw it down anyway. There's two. And then for our liquid, we'll draw this line straight down. All right, so there's three. All right, so our C alpha, we can get it, pull straight down. It's around, we know this is 8 here, so and it passes through this point. So we can pretty comfortably say C alpha is equal to 8. Right, our C naught, our C1 of our sample, C1 is equal to 30, right, because we defined that. And then our C liquid, about, I don't know, we'll say 42%. Right, all these are weight percent silver. Okay, so we want our fraction of our liquid phase. So fraction of the liquid phase is going to be the length of the opposite side from liquid divided by the total length. Right, so fraction of liquid is going to be equal to the opposite side, right? C1 minus C alpha divided by the total length, C liquid minus C alpha. Right, so this becomes 30 minus 8 divided by 42 minus 8. This becomes 22 over 34. Right, so our fraction of liquid is 22 over 34. It is about 0.65. Or 65% liquid this is by mass. Right, if we're talking about weight percents, then this is liquid by weight, right? If we were dealing with atomic percents, that would be liquid by volume. Okay. All right. And we could, similarly do the same thing for fractional amount of alpha. It would just be the short side divided by the long side. Okay, I want to do one more example. And we will use a new phase diagram. This is one we will see later in class, but this is the iron-carbon phase diagram, also known as the steel phase diagram. Right? We have pure iron on the left. We have weight percent carbon on the x-axis, and we have cementite at 6.7 weight percent carbon. So this plot is actually not the full phase diagram, but for a lot of steels, we're talking about really relatively low carbon concentrations, so we focus on these small values here. Right, above cementite forms at 6.7, right, above that the metal gets extremely brittle, so it becomes not as useful as a metal, so a lot of steels stay on the low side of the carbon concentration. But okay, just looking, right, we have cementite, which is, we're aware of that. Right here on the left, this very, very small region here, we have ferrite, our alpha iron, right? and we have austenite, which is a gamma iron at a moderate temperature here. All right, down here we have our alpha plus Fe3C. You know this. This is our pearlite. Right, but at high temperatures, right above this 727 degrees Celsius, we have austenite plus cementite there. Okay, so let's say we have an alloy at 3% carbon and 1000 degrees Celsius, and I would like you to tell me our fraction of cementite. So Fe3C. Okay, so we know what to do. We draw our tie line. Right, that connects. Okay, we have our gamma composition, right, which we draw straight down. This is our composition of our gamma phase, which is about, I'll say 1.6 weight percent. Right, our cementite, we don't have to draw a line straight down, but let's do it anyway to give us practice of drawing lines. And that's a bad line. This is the composition of our cementite. Right, it is 6.7 weight percent. Right, and then our sample itself, right, C1 is 3 weight percent. Okay, so fraction of Fe3C, right, is the length of the opposite side of Fe3C, right, divided by the total length. So it's going to be this length here, right, divided by the total length. So where am I going to draw it? I'll draw it here. So fraction of Fe3C, right, it's going to be equal to this length here, which is going to be C1 minus C gamma divided by the total length, which is C Fe3C minus C gamma. All right, we'll plug in our numbers here. It's going to be 3 minus 1.6 divided by 6.7 minus 1.6. Okay, this should be 1.4, and this becomes 5.1, which gives us a fraction of 0.27. So 27% of our microstructure we expect would be cementite by weight. Okay, so that's basic lever rules, right? You can do it for basically any two-phase region. It's quite handy and quite fast. It's not too hard. One more special case that was brought up that I would like to mention is you can also do lever rule for special microconstituents. So if we go back to the copper-silver phase diagram, we have this unique transition here, right? This eutectic transition, which is a liquid to alpha plus beta. It's a liquid to two different solids without entering a two-phase region, right? We don't enter an alpha plus liquid and we don't enter a beta plus liquid phase. We go directly from one to the other, right? And that gives us our fun eutectic microconstituent, which some of you have probably seen in the lab by now, right? And they give us the composition this occurs at. It's at 71.9%, right? So, say we had an alloy which was a hypereutectic alloy, let's say 80% silver at 500 degrees Celsius, right? 80% at 500 degrees C. This microstructure, assuming we cooled from a liquid, right, is going to have, initially starts as a liquid. As we cool, some of the liquid is going to transform into beta, right? So we'll have a beta plus liquid. And then when we hit this eutectic temperature, right, the remaining liquid is going to transform into eutectic, alpha plus beta, right? So our final microstructure at this point is going to be partial beta and partial alpha plus beta, right? So say we had these conditions and I asked you, what is the fractional amount of eutectic microconstituent versus beta microconstituent? Right? So what is our fraction of eutectic? Okay. So now we're treating it, instead of two different phases, we're treating it as two different microconstituents. One is beta, right? And then one is eutectic, alpha plus beta. So we can still do the lever rule on this, except now, instead of drawing between the alpha and beta, we're going to connect the beta phase and the eutectic composition, right? Which is the composition that eutectic forms at. Okay? So we draw our tie line, right? We know the composition of the eutectic portion of our microconstituent is 71.9, right? So we can call this C EU for eutectic, right? We know the composition of our alloy, right? That's 80%, that was given, right? So C1 is 80%, right? And the composition of the beta, right? Draw a line straight down, right? This is our C beta, and I don't know, what is that, about 90, I'll say 97% silver. Okay, so we have three compositions, and we say what fraction of our microstructure is eutectic, right? And we can use the lever rule, fraction of eutectic, right? You've probably got it by now. It's going to be the length of the opposite side of the eutectic, right? So it's this length, right? This length here, divided by the total length, okay? So it's going to be C beta minus C1 divided by the whole length, C beta minus C eutectic. Okay, plug in these numbers. We know what these are. This is 97 minus 80, right, divided by 97 minus 71.9. This gives us, I can do that top one, 17. 97 minus 71.9, that is 25.1, okay, which is, that fraction is about 68, 0.68. So 68% of the microstructure is eutectic. All right, and that's what we're looking for. And what this means as a partner statement, right, is that 32% is going to be beta phase that formed before the eutectic. So 32% is what we call pro-eutectic beta phase. Right, and the pro means before, so before the eutectic. All right, so you can have pro-eutectic beta, you can also have pro-eutectic alpha. But again, we still use the lever rule for each of these. I hope that cleared up any confusion that you had, or if you didn't have any confusion, I hope this reinforced your already steady knowledge. I'll see y'all in the classroom and in the lab.